Hi everyone. Today we are going to move on to start a new topic, which is SVM, and that is for support vector machines. Well, that is a very hard topic probably when I started doing machine learning, and well, thanks to Scikit-learn, well, it makes the SVM much easier. Okay, so well, first we have to understand what is SVM, or especially what is a support vector, right? So if we want to consider the irises set and we only consider the x and y axis to be petal length and petal width, and we only consider two classes, versicolor and the setosa. Okay, so if we want to draw a class boundary to distinguish or separate those two classes, and we can do the pink line, here, or we can do the red line here. So for both lines, and they can be considered as the boundary between two classes. And of course, if you want to do the green dotted line, that doesn't work, right? So for those two lines, the red line and the pink line, which is better? Well, to answer this question, how about we do that in another perspective, which is instead of only draw one line to separate those two classes, how about we want to draw a margin? Okay, so and then it becomes the graph on the right side. So our target becomes we want to draw a margin between two classes, and then this margin should be as wide as possible. A wider margin means that if we draw a decision boundary right in the middle of the margin, and then it should be the best separation of the two classes. Okay, and then for those samples, well, which defines the margin, and then we call them support vectors. Okay, so in this case, well, the first point is, well, those two classes, they are indeed linearly separable. Okay, so we want to just try to find the largest margin possible, and then the samples defines that margin. The samples make this margin can no longer be widened, and those samples are the support vectors. And remember, when we are finding this kind of margins, and this classification is also sensitive to the scale of the features. So in this case, we should probably use the standard scalar. Okay, so in this case, well, remember the last machine learning algorithm, we do need the standard scalar was k-nearest neighbor, right? So in this case, in SVM, we need to use standard scalar again. Okay, so the next topic is, well, if we always want to do a hard margin classification, which is we want to draw a margin and then we want to perfectly separate two classes, that is not always doable. So for example, if we add a yellow sample here, and that is an outlier, and then those two classes are no longer linearly separable anymore, so we can't do a hard margin classification. And in another case, if we add another outlier right here, so those two classes, they are still linearly separable, but the problem is with only one outlier, it will push the boundary all the way to the right side. So that is wrong. We can't allow one outlier define where the margin should be, right? So in this case, the hard margin classification doesn't work very well, and then we want to do a soft margin classification. And for the soft margin classification, and we are gonna allow a few of the samples stay right inside of the margin we define, and they are going to be considered as support vectors. Well, however, we are trying to be tolerant on some of the outliers, and we don't want the outliers to define our margin 100%. So how do we control that? And then we have the C hyperparameter. So a small c hyperparameter leads to a wider straight and then more margin violations. And on the other side, if you want to do a high C value, and then well we will allow fewer margin violations, and then the margin will also tend to be narrower. Okay, so let's load the array set, and then we only pick two columns, and we want to create a pipeline. So for this pipeline, we are sending two components inside. The first one is a scalar. We want to create a standard scalar, and the second part is we want to do a machine learning model, and we are doing a linear SVC model. Okay, so we just create a pipeline, and then we train the pipeline, and after that we create a fake sample, and then we want to do a predict, and our model says it belongs to class 1. Okay, and when we are doing the linear SVC model, it's very important that eventually we are going to draw a line, and which is the center of the margin, right? So when we are drawing a line, and then there are two important attributes, coefficient and intercept, and this is how we define a line in the x and y axis. So we created function which draws the decision boundary, and we want to do a standard scalar, and this time we want to try a very small c and a very large c, and we want to see what are the differences. So we created one pipeline with the first the linear SVM, and we also created another pipeline with another linear SVM. Okay, and well, you want to pay attention to this part of the code. The reason is, well, when we are doing the linear SVM, we need to transform the data using the standard scalar, right? And later, after we train the linear SVM model, we want to have the support vectors, and we want to plot the support vectors into the original x and y axis. So let me jump down to the image we are producing to explain why. Okay, so let me just use the left side as example. So we use the petal length and the petal width as the x and y axis. However, when we send the x and y, when we send those features into the standard scalar, those two features will be changed for sure. And when we get the support vectors from the linear SVC, and that is already on the scaled petal length and the petal width. However, if we want to highlight the petal length and the petal width of the support vectors, we have to put them back into the original scale of the petal length and the petal width, and we need to use this part. Where is it? Okay, we need to use this part of the code to convert back from the scaled features to the unscaled features, so that we can highlight the support vectors. Okay, so let's move down here, and okay, after we have finished the linear support vector model, and we want to plot the decision boundaries of the two models with c equals 1 and the c equals 100, and then you see the difference. So for the c equals 1, and we have a larger or wider margin with more margin violators. And if we want to use a higher C, and then we will end up with a narrow margin with a few violators. So which one do you want to choose? And well, it really depends on the data. If you know the data is beautiful enough, and probably you don't want to use a very small C. And on the other side, if you suspect the data is very noisy, and then in this case you do want to use a very small C. So well, here is a question. If you find a soft margin linear SVM classifier got influenced too much by a few outliers, do we want to increase or decrease the C value? So think about that. So let me just give you this one as an example. Well, if you are seeing the decision boundary is pushed away just by one outlier in this case, do you want to try to increase the c-value or decrease the c-value? Okay, the answer should be we want to try a smaller c-value. The reason is, well, the more violators or the more noise data we have, and then the smaller the c-value we should try. We need to allow more samples stay on the street on the margin we created using the linear SVM model. Okay, so I'm going to pause the video here and I will see you in the next video.